Okay, my wonderful students, let's go. Glad to see everybody here. Um, we're going to talk about some news to start. Black holes were in the news today in the past few days. They've been egging us on the first ever picture of a black hole. Now, as somebody that's my research area, I can tell you they're never ever going to get a picture of a black hole. But what this shows is all the stuff around a black hole that you can see. And then in the middle, you don't see anything. So what this is, you know what this is? It's like the rings of Saturn. You know, they swirl around Saturn and stuff. Now, you know, eventually they're going to go in and crash into Saturn and stuff. The ring or disk, as they call it, around a black hole is called an accretion disk. And it's sucking in matter from other stars that may happen to be nearby. And as it swirls, and you know, and just like Saturn, it's going to have some angular momentum, so it's not going to go straight in, most of it. So it's mostly going to swirl in. And as it goes, it gets more and more compressed. It gets hotter and hotter. And because it's hot, it emits a lot of infrared all the way up to X-rays and gamma rays. And this is a false color. I believe this is infrared images of the accretion disk around a black hole that's approximately 6.5 billion times the mass of our sun. So that's a big one. We don't know how they form. We know that there are black holes that we've seen nearby, like Cygnus X1, a few times the mass of the sun. We think that those happen after a supernova detonation of a bigger star, blows most of itself apart, but leaves behind an iron core that collapses into a black hole. But we don't know how these form. Now, there's another one that they're trying to image in the same way at the center of our galaxy. This is this galaxy known as M87. So millions of light years away. The center of our galaxy, we have one. It's not quite as big. It's a few million times the mass of the sun. But we watch it in infrared. We've bagged it. We've bagged it basically by looking at Kepler's third law. So they've bagged the mass of this baby by analyzing as much as they can. And the interesting thing about this one is a set of telescopes is interferometric. In other words, they use them at a set of telescopes wide apart, thousands of miles apart, as something called an interferometer. And what they do is they combine the light signal, or in this case, infrared signal or radio wave signal. It's actually infrared microwave region. And they combine the signal from two things thousands of miles apart, and then they add them together, and then they adjust the distance, they judge the distance by the amount of constructive or destructive interference when they combine the two signals together. And that's how they figure out, and they get a stereoscopic view of this thing. So here's a picture of a telescope down South Pole, down in Antarctica, with the happy feet. So we're going to probably be seeing more about that black hole and other ones in the days to come and the years to come. It's kind of exciting. But it's interesting for us that it's using an interferometric or electromagnetic interference effect to get clarity and resolution of a very, very far away object in the center of another galaxy. Very difficult task, but they've done it. All right, let's dip back into chapter 1611 on interference. We're going to talk about intensity of wave energy. And I like this picture. It's from Astronomy Picture of the Day. Here's the URL for it. It shows a star here towards the center. It's a young blue star. It's a little bit more massive than our sun. And it's very hot. It's about 20 times the mass of the sun, if I recall correctly. It's very hot. It has a very hard solar wind, although we would call it a stellar wind because it's not the sun. And that stellar wind is causing shock waves in this surrounding interstellar medium. And so that's what this big, let me get my cursor over here. That's this big slash through here. That's all generated by this little star here. Okay, so there's a lot of mayhem in that. And there's lots to be discussed about the intensity of that. Let's go to a picture from the textbook. This is figure 2 in chapter 16:10. A couple stereo speakers. And what they've got it mapped out, the two stereo speakers are emitting a pure tone, same wavelength, same pitch, same frequency. Okay, and so the waves, in a sound wave, the air becomes more dense and less dense, or rarefaction and compression. So these dotted lines are where air is a little bit lower pressure. The solid blue line is where it's a little bit higher pressure than the ambient air pressure. And then here's another rarefaction, and it goes out from the speaker in each direction, same with this speaker over here. All right. Now, where the compression or overpressure coincides at the same location, you have peak intensity. Okay, so that's constructive interference. And they've mapped out these kind of reddish, purplish blobs a few places around here to indicate. Now, these are constructive interference, and the sound will be intense there. So if you sit yourself right here, you're going to hear things very clearly, nice and loud, and with clarity. Now, if you go over here where you have a mixture of rarefaction and overpressure, compression, you get zip-zap. That's like a crest interacting with a trough, flat water, baby. You don't get zip. Okay? If you're sitting there. Now here's the interesting part. You know, there's a bunch of other, nodes here where you don't get any sound. But your ears aren't, your ears are going to be bigger than, so you'll probably hear a little bit. But theoretically, these points here, you don't get zip zap out of them. And here's something that I found kind of interesting. You can also get this effect in a long tube. An organ pipe, when you push air through an organ pipe, it'll blow a certain note. I mean, if it's the right length and the right diameter, you'll get middle C or high A or, whatever tone you want. And some really deep ones on, the organs, those big organ pipes, they really put out the low, the low bass notes. Now, one time I was in a new building at Montana, the Engineering Physical Sciences building, and they had just built it. And in the basement, the engineering people had the basement, and the physics people had the ground floor and up to the third floor. And so I was up on the third floor, and I rode the elevator up to the third floor, and I was walking all the way the length of the hallway to my office, my grad student office, which was at far end. And I noticed as I walked through the hallway that I was walking between constructive and destructive, because there was a sound, very low, a bass, going through that hallway. And every 4 or 5 steps, I'd go from loud to very faint, then back up to loud and very faint. And I thought, oh my goodness, this is some kind of a resonance, like an organ pipe. And what I found out later, I was telling my buddies about it, and they said, come on. They didn't call me Dr. B at that point. They called me by my first name. Come on, Thomas. And I said, no, man, that's what I heard last night. And I later found out that the engineering department, what they had in the basement was a big wind tunnel. So they were running their wind tunnel that night, and so they were sucking air into the wind tunnel and then back out. And apparently that part of the airflow was up in the third floor, probably the other quarters of the physics building. And so we did have an organ pipe, a big, huge organ pipe. It's kind of cool. All right, so I highly recommend you look at this. Now, the key here is that the null where you get zip zap is halfway between constructive loud spots. There's an example there. Now, so here's the loud spot here, this reddish purple blob here, where the two streams of sound first intersect, and then here's this one down here, and right between them is a point of zip zap. In other words, a null in the sound field. All right. So let's talk about intensity. All right. Now, the basics, as we've talked about before, waves transport energy and momentum. And frequently they do it in many different directions over a wide area. And it was 20 times the mass of the sun. See, and here's the scale. Look at this. This is 1 light year up here. So this is a big picture. And here's this little old star, and about a light year away is this shock wave that it's creating itself. Now, 1 light year away it's got to be fantastic. Fantastically hot and a very strong stellar wind, because 1 light year away from the sun, you're not going to feel jack from the sun. I mean, the sun is pretty average. There's no great shakes about it. But this one, it's got a lot of, here's the name of it, Zeta Ophiuchi, in the constellation Ophiuchus, which, I don't know, is somewhere near the zodiac. I'm not too familiar with Ophiuchus. I haven't memorized that one. But anyways, so here's this thing, and it's going, you've got wave energy going out from the star in zillions of different directions and distances and stuff. So the way that you rate the intensity is you have to set up a catching area, some fiduciary area where you say, all right, I'm going to count the number of joules of wave energy per second that go through this fiduciary area. So you can make it a square meter, a square centimeter, a square light year, a square kilometer, anything you want. Okay. Now, and so you count the number of joules of energy going through there. Now, for instance, a solar cell, the amount of joules hitting a solar cell out on a bright sunny day is proportional to the number of volts that you get out. So the more volts you get out, the more joules of energy that are hitting that solar cell. Now, solar cells are not going to be a square meter or anything. But what we normally do is just count joules per second per square meter for the intensity. And it's not graven in stone. That's the only one, but that's the one that it's metric, and that's the one we're going to be talking about today. Joules per second. Now, as I think I mentioned before, 1 watt of power is a joule per second. So write that down. 1 watt, capital W for watt, equals 1 joule per second. So that's the definition of the watt, which was named after the steam engine guy, Watt, that made steam engines and stuff like that. So 1 watt per square meter. And, our sun puts out about 1,300 watts per square meter into the top of our atmosphere. So if you go above all the clouds, all the atmosphere, so a little bit higher than the space shuttle. Space shuttle is orbiting. There's actually a little bit of atmosphere up there. It's very thin, but they can measure it. And it's a little bit higher than the space shuttle. The amount of solar radiation, I think it's like 1,367 watts per square meter, if I remember correctly. And it varies a little bit, depending on sunspots and, solar prominences and stuff like that. But it's about 1,300 and change. So here's your reference area. Here's your star, or whatever else it is that you're trying to study. So the intensity, power divided by area. Okay, so that's watts per square meter. So the units of intensity are watts per square meter. And that's good. Watts per square meter, we use that with the solar constant. 1,300 and something watts per square meter at the top of the atmosphere. On the sunny side of the Earth, if it's facing straight, 1 square meter is going to catch 1,300 and something watts. So it'll power a hair dryer or a microwave oven or something like that. 1 square meter of solar cells. Now, let's make a little more room here. The decibel system is actually based on ratios with some standard fixed agreed upon intensity. So you take the intensity of whatever you're measuring, and then you compare it in ratio to a standard intensity, and then you take logarithms of it. It's pretty nasty looking. Here it is. And it's whatever the log of the intensities is times 10. Okay, so if your intensity is 100 times I0, then that quotient is 2, or the log of that quotient is 2. So your decibel difference is 20 compared to the baseline intensity I0. Now, the way that they've defined I0 is the threshold of human hearing, right? So they think that for most people, unless you're like Spider-Man or something like that, about 1 times 10 to the minus 12 watts per square meter is about the threshold of energy. If you get that much or more from a sound wave, pounding on your eardrum, you're gonna, that many joules per second per square. Now your eardrum doesn't have a whole lot of square meters. Okay, it's a very small fraction of a square meter. So this seems small, but it's not really that small, right? And if you think about it, let's see, a millimeter is 10 to the third, 10 to the minus third of a meter. So a square millimeter is 10 to the minus sixth of a square meter, a millionth of a square meter, all right? So your eardrum is going to be a few tens, a few dozens of square millimeters. Have you guys ever have had an anatomy class? Have you ever dissected an eardrum, an ear? Do you know anybody? Bueller? Anybody? Semicircular canals. What's the diameter of semicircular canals? Anybody know that? Or a few millimeters? Maybe 2 millimeters? All right. So you're talking maybe a few dozen square millimeters. So that means you have 10 to the minus 5 of a square meter. All right. So that's in the denominator here, 10 to the minus 12. So that means the numerator has to be 10 to the minus 7 watts. So that's 1/10,000,000th of a watt. Now that's pretty low, but a milliwatt is not. 1,000th of a watt, a milliwatt is something, these little clickers that you get, they have a little teeny bulb at the end for your keychain, and you can look at, your doorknobs, you're putting your keys in and stuff like that. That might be a few milliwatts power. The lights on your dashboard in your car, maybe a few milliwatts. Those things are by design low wattage, bright but low wattage, so that they don't burn up your battery. So that's the decibel system. Here's the table. You can go ahead and look at this in chapter 17.3, table 2. And you can see up here at the top, 0 decibels, threshold of hearing. All right, let me put on my specs here because this is really small on my screen here. Okay, 10 decibels. And here's the intensity, and the decibel levels here, 10. That's the rustle of leaves in the forest. 20, whisper at 1 meter distance. Okay, and on down here, they have a classroom lecture. 80 decibels right here, classroom lecture. Okay, so that was me blabbing my big mouth. Okay, 90 decibels inside a heavy truck, and so on and so on. And then down here, bursting eardrums, 160 decibels. And there's actually a limit there is a decibel level. I can't remember. I calculated it once. The loudest possible sound in the atmosphere, and that's a sound where the distance, the amplitude, is equal to atmospheric pressure. So you have an overpressure twice the atmospheric pressure and an under pressure of 0 atmospheric pressure. So that's from a vacuum to double the atmospheric pressure. That would be, yeah, and that's hard to achieve except, with some kind of a nuclear weapon or something. So anyways, let me just invite you. Read chapter 17 on hearing. Those of you guys that are trying to get into med school and PT school and everything, you might enjoy reading about it. And you have the tools. I mean, you should be able to read it easily if you care to do that. But I'll, the final exam, I'll have a question about decibels and something basic on that, but not a whole lot from 17, just this table basically. All right, let me pause for questions. Yes. Yeah, I mean, if I'm going to ask you decibel questions on the test, I'll probably put that on the cover, that table on the cover, or a slice of it, like the first 5 lines or the first 2 and then the last 2 lines. But being able to think about intensity and what decibels are, So, yes. Repeat. The reference area is square meters in the units that we're using. Watts per square meter. That's just but it's an imaginary surface. But so if you're trying to figure out how many watts actually hit your eardrum, you have to factor in the area of the eardrum. That's why I was trying to mentally estimate, a few square millimeters or so, maybe 1 square centimeter. It's a bigger. I'd have to ask it ear, nose, and throat doctor, I guess, on that. Question? Yes, Rachel. Yeah. So this formula here, beta, that's the decibel. Okay, so you look up the intensity, or you try to measure the intensity of sound coming from, a jet engine. Okay, and that's going to be so many watts per square meter. Okay, then you ratio it up with 10 to the minus 12 watts per square meter, I0. Then you take the logarithm of that, and you multiply that by 10, and that's the decibel. Right? So that's why this table here has the decibels and the intensity in there. So the intensity, if you notice here, the intensity goes up by a power of 10. Okay, and the decibels go up by 10. So decibel, it's basically a logarithmic scale. Okay, and everybody loves logarithms, so. Mm-hmm. So I might ask you about that. But remember that you have on exams, you always have matching formulas and stuff like that. Remember, what I want to do on exams is to test your ability to think, not to look up stuff on a table and memorize it. Don't worry about memorizing this. If you need it, it'll be on the cover page. Martin, what's the area based off of? Nothing. It's based on a hypothetical square meter, as I already, mentioned. Okay, so that's, it's like asking me, well, I'm watching a snail move at 0.01 meters per second. Where's the meter? Well, you don't need a meter stick to measure 0.01 meters per second. But if you did, I mean, you would take, 100 seconds for it to, actually, that's pretty fast for a snail. 100 seconds to move a meter, that's a supercharged turbo snail. But you don't need so it's just kind of a hypothetical thing, all right? But the real thing that is that damages your eardrum are the joules per second. The amount of energy that it absorbs. If it absorbs too much per second, it's going to blow your eardrum. Okay. So just saying decibels, just saying intensity is one thing, but if you're really up close to it, then you know you then you factor in the area of your eardrums and whatnot. So, but then there's only one thing here. Down here, this is implicitly factoring in the area of the eardrums surface, and down here as well. So, but the other things are just people talking, leaves in the forest, etc. Now here's Amadeo Avogadro from Avogadro's Constant. And he says, read chapter 17 if you're interested. But for us, we're going to go back to, I believe it's chapter 11 now, fluids. We're going to talk about some basic stuff here about fluids. Fluids are things that flow. So now steel is a solid, but if you heat it up to a high enough temperature, it'll be molten, it'll flow. All right, so a given substance may have fluid characteristics depending on the temperature and the pressure. Even hydrogen gas can be solidified. So, a gas is a fluid, but you can solidify hydrogen, metallic hydrogen, very difficult to do. But we know that it can be done. Now, the F equals ma and momentum and kinetic energy and everything else of zillions of atoms and molecules encode various levels of interatomic and intermolecular interaction. Okay, so those things, the molecules and atoms of a fluid interact by collision. If it's so you may or may not have crystalline bonds. If you have crystalline bonds, of course you don't have a fluid. But if you don't have crystalline bonds, you may have a liquid. So a liquid like water has a hydrogen bond. Okay, that's how water droplets form. It's weak, but it's enough under atmospheric pressure at the surface of the Earth to make spherical droplets of various sizes. Okay, so and you can have vapor or a gas state of a molecular substance like water vapor, or it could be a monatomic gas like helium. Just a bunch of little helium atoms flying around. All right. Now, fluid exerts a pressure. Here's a water cannon. This is over in Turkey some time ago. They were, for crowd control, they were using this water cannon. This guy's taking a shot. And a water cannon, that fluid pressure, it'll deliver a punch. So what does that tell you? A little bit of F equals ma from a fluid. All right? So you can't do a fluid you can't use a water cannon if it's going 1 meter per second. You've got to put some zip to it. And you can't do it, you can't deliver a lot of momentum to some guy standing out in the street that you want to knock on his keister, or at least get him to stop, running forward. You can't do that without delivering some momentum. So you have to have more than 1 milliliter per second coming out of your water cannon. So the density, the velocity of your object are all factored into the pressure of the fluid. Now, I'm going to ask you a clicker question. Go ahead and get your clicker out. Turn it on. Let me turn mine on. And I'm just going to ask you an informal question, and hopefully you'll be able to figure this out concerning a generic idea of pressure, and then we're going to try to apply it in our next few slides. All right, so get your clicker, turn it on, get a go nitro. And let's go to the next question. Here we go. Which puts more pressure on the floor? Normal sized woman wearing stiletto heels, or an M1A1 Abrams main battle tank? 20 seconds to vote, starting right now. Let me see what you guys are voting for. Uh-oh. It's a binary solution set, and there's an argument between the two answers. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Well, it looks like, let me check my specs here. 59% of you voted for the M1 Abrams tank. So raise your, no, don't raise your hand if you wrote that, because the answer is actually the stiletto heels. And guess what? Only 41% of you answered that. Yeah. And here's why I know that. I have a friend in the Air Force, and he's retired now, but he's told me, you know, he was a sergeant, and he was detailed to load these big monster aircraft with tanks and stuff and ship them off to, you know, wherever they were going, to Guam or something. And he said, we put those big Abrams tanks up there, no problem. The floor is designed for that. But we had to tell the female officers, do not wear your high heels into the, because they would, sometimes they would take the same plane, they transport, you know, GIs. And they had to tell the lady officers, do not wear those heels. You got, because they're going to poke a hole through the floor. The same floor that'll hold up a battle tank won't withstand, you know, the stiletto heels. It's kind of amazing. And it's just, so that gives you an idea of what pressure is. Force per unit area. Go ahead and write that down. Pounds per square inch, PSI. You know, and if you're a scuba diver, you've heard that. You fill up your tanks to a certain pressure with compressed air. Now, so many PSI, so many atmospheres. And it's really based on, let me get this off the screen here. It's really based on the exchange of momentum. So the extrinsic pressure that we measure, you know, like with your pressure gauge for your car or your bike tires, you know, you go to Wawa and get free air. You dial in 33 PSI if you're in America. Right? That's really encoding the exchange of momentum from zillions of molecules and atoms that ricochet off the wall of the container, you know, the wall of the tire. And they push it outward. So there's an exchange of equal but opposite delta P's with the wall. So these two oxygen molecules, for instance, the delta P of the molecule is to the left, you know, so many kilogram meters per second. All right. And that means that the wall takes this much, the same amount, but outwards. And it's got to be rigid enough to provide, and if it's not, it'll expand like a balloon until it does provide the right amount of inward force. So we measure pressure as PSI, pounds per square inch. You know, so many molecules per second. So that'll be delta P per second. That'll be a force divided by the area, and that's a pressure. Okay, pascals, that's the metric unit. So if you go over to Europe or something, they're going to have bike tires rated in pascals, or actually kilopascals, I guess. 1 Newton per square meter. Bars and millibars, like on the Weather Channel, those are related to atmospheric pressure. Atmospheric pressure 1.00 atmosphere is officially set at 1013.25 millibars. And that is the official ambient air pressure at sea level on a fair day. Now, if you go up to Denver, fair day, same temperature, the air pressure is going to be less because there's less atmosphere. You're a mile high, so you don't have as much atmosphere up there pressing down on you, right? And so if you go up to the top of Mount Kilimanjaro over in Africa, the way people have been doing a lot, even less pressure. You know, Kilimanjaro is high enough that I think that's half the atmosphere is below the peak, and half the atmosphere roughly is above the peak. Now you go to Mount Everest, you've got a lot of atmosphere below you and not much above you, and that's why it's so hard to breathe. There's oxygen up there, but every breath that comes, it's hard to get that stuff into your lungs because you can't, you know, it's so much less pressure. Now, it's easy to get a lung full of air down here, but sucking your hose up there on Everest is quite another subject. Let's do an example. Let's take 20, you know, this is something that I have tried to do, and faculty here I have seen try to do this. You know, shoot a bunch of tennis balls at a piece of plywood and try to exert enough force with the tennis balls per second to get it to stay. But we're going to do it, you know, in a thought experiment here. So we're going to throw tennis balls at a 0.8 square meter surface and you try to exert some force on it. So here are the specs. The mass of each basketball or tennis ball, 0.056 kilograms. And we're going to give it a speed of 10.3 meters per second, just to give it a, so that's like 20 something miles per hour. Okay, granted to do that. Okay, angle, and we're going to shoot them perpendicular to the surface. So what that means is the ricochet is straight back. So we're not going to do any trig on this one. All right, and we could, you know, the previous diagram we had to come in at an angle. Okay, but this one we're just going to go straight back. We're going to have 20 of them, and it's going to happen in 1 second. So the amount of momentum we deliver to that thing and the amount of delta P that we deliver, that's what we want to calculate. And that'll be the basically the size of the force, because that's what happens in 1 second. So delta P over delta T is the net force, and then it'll be spread over 0.8 square meters. So let's work this out. Okay, the momentum on the way in is 0.056 times 10.3, and that works out to 0.56768 kilogram meters per second. Boring. We've done this about 5 million times, but now we're using it, and we're using it in an example that's to illustrate what we think is happening with the molecules of air that we cannot see. All right, so there's your first momentum. Outward momentum, we're assuming it's a good bounce, and you get the same momentum backwards. Negative 0.5768 kilogram meter per second. And that's perpendicular to the surface of this piece of plywood. Excuse me. All right, so there's your P in, your P out. So P out minus P in is your delta P, and that's negative 1.1536 kilogram meter per second. That's your delta P. All right. Now, multiply that by 20, because that's just one tennis ball. All right. So you got 20 of them per second. All right. Now the per second is going to turn this into a force. And that's the force delivered by one tennis ball, then we multiply it by 20. So go 20 times that, and then divide it by a second. That I like from chapter 16. Here they are. Go ahead and jot these down, and you can use those to study and wrap chapter 16. And with that, you're dismissed, and I'll see you guys next time.